All right, this is a little tutorial on graphing motion, so you can look at those graphical relations between distance and time and velocity and time so that we can get accelerations and velocities. So if we look at a distance versus time graph, so distance is the y-axis, time is the x-axis, the slope of that line is going to give you the velocity because distance divided by time is equal to velocity, as we've mentioned before. Now, more specifically, let's look at a for instance. And so this is distance versus time for three different segments. So we got a segment A, B, and C, and we want to answer these questions. So it says, the graph shows the position of the car with respect to time. Does the car ever go backwards? Looking at the graph, sections A and C both have positive slopes, but section B has a negative slope. So the car is actually going backwards in the segment labeled B. So our answer choice would be B. It's going backwards in that particular segment. Is the instantaneous velocity at point A greater and less than that point C? So this segment versus this segment, what you have to do is look at the slopes. Looks like the slope on C is a bit steeper than the slope on A, so that means the slope would be higher, meaning the velocity is higher. So A is a little bit less than C since we're comparing A to C. Now, if we do the same type of thing with acceleration, we plot velocity on the y-axis, time on the x-axis. The slope of that line is the acceleration. That is how much speed am I picking up, or if I'm slowing down, how fast am I slowing down? Now let's look at a, for instance, graph on that. We got segments A, B, and C. So is the velocity constant at any time interval? All right, where is it flat? It looks like it's flat in segment C. So the answer to the first one would be segment C. The velocity would be constant. And which segment is the acceleration the greatest? Okay, where is it the steepest? Looks like maybe it's a bit steeper in segment A as opposed to segment B. It's not accelerating C, so that's not a good answer. If we look at the same graph, just a couple more questions. If a car moves along a straight line, does it ever go backwards? The velocity would have to be negative for it to go backwards. So the answer would be no, it does not. It goes forward at a little bit faster rate, goes forward at a little bit slower rate, continues going forward at a constant rate, but to really go backwards, I would have to get into the negative velocities down here, and the graph never goes there. Now, during which interval is the distance traveled the greatest? You're going fastest in C, so it likely you're going the fastest on that particular graph. This is just sort of a, there's no numbers, but you're going fast at the period of time you're going fastest, you're likely going the farthest. It depends on how long you travel that fast and some things like that. Now let's look at a, for instance, with some numbers. So we got time intervals on the x-axis at 2-second intervals and velocities on the y-axis at also 2 meter per second intervals. And so we'll have to bring in some white paper so we can actually run some calculations. But what we find is that we have constant acceleration between 0 and 6 seconds, and then another constant acceleration between 6 and 10 seconds that's different than the first interval. So we want the average between 0 and 6, and then 6 and 10. So if we look at our acceleration between 0 and 6, it's going to be change in velocity over change in time. And so my velocity between 0 and 6 goes up to 4 meters per second minus 0 meters per second because it started at rest. Then how much time elapsed? 6 seconds. So essentially you got 4 divided by 6, which is essentially 2/3, or we'll call it 0.67 meters per second squared. So that's for number 1. For number 2, we're looking at that 6 to 10 second interval. So acceleration is still delta v divided by t. And so at the end, you're going 10 meters per second. And then at 6, like we said, we're going 4 meters per second. And we did that over 4 seconds. And so we got 6 meters per second over 4 seconds. So 6 divided by 4 is 1.5. So the acceleration in this particular case is 1.5 meters per second squared. And so that gives me the answer for question 1 and question 2. Now, question 3 asks, what's the average acceleration between 0 and 10? That is the entire graph from here to here. So essentially, we'd look at a line with a slope right here. And it'll be between those two numbers, but probably not a direct average of those two numbers. So for question 3, we still got acceleration equals change in velocity over change in time. But now we're going from 10 meters per second at 10 seconds minus 0 meters per second to begin with. The whole scale is 10 seconds, so that's a 10-second interval. So we got 10 meters per second divided by 10 seconds, or 1 meter per second squared. So you notice it falls between those two, but it's not a direct average, which kind of brings us to the 4th question. Why is that not the case? And it's because these time intervals are not equal. One is 6 seconds and one is 4 seconds. And so it's not going to be an even average unless you're accelerating even amounts of time. This was a brief tutorial on graphical relationships of motion.